Now we will learn random variable. Random variable is a measurable function from sample space S to real number R. To understand the measurable function, we need to know the sigma field. So, let us record the sigma field. So, sigma field is defined on a non-empty set. Suppose S is a non-empty set, suppose S is a non-empty set, suppose this is the S set, and we consider a collection of subset of S. Suppose this is denoted by C. So, let us consider one example. Remember the random experiment. Random experiment, suppose we are considering random experiment. This is tossing a coin. Tossing a coin. So, then if you tossing a coin, so then what will be the outcome? What are the possible outcome? In which run, whether head will come or tail will come, we do not know, but we know all possible outcomes, that is head and tail of this random experiment. So, then S is the sample space containing all possible outcome, head and tail. So, for defining sigma field, it is not required any random experiment, just we are giving the example here. So, any non-empty set you can take, S can be R. Here we are considering this set S is equal to head and tail. So, C is a some subset, collection of set. So, we can consider this set, so subset. So, suppose C contain two subset only, suppose null set also a subset of S, and also S is a subset of S, it is also a collection of subset. Also you can suppose, let us take another, suppose C2 is considering phi, then H and then S. So, we have just included another subset, H is another subset of the S. Now, sigma field defined as, so C is a collection of subset of S, subset of C is a collection of subset of S satisfying some property. So, a sigma field, a C is sigma field if the following conditions are satisfied. So, following properties, we can say properties are satisfied. So, following properties are, so what are those properties? One is that the sample space, sorry, this is the set we are considering non-empty set, from where we are taking the collection of subset of S, So, one property is that S has to belongs to C. So, S also a subset of S. So, you can consider S or not, but here if C has to be sigma field, then S will belongs to C, and if any set A belongs to C, that means A will be a subset of S, then A complement also has to be inside C. So, A complement also in C, and third condition is that if A1, A2, An countably infinite collection of subset of S, those are element of C, are in C, So, that means AI belongs to C for I is equal to 1 to n dot dot infinity. So, not only up to n, it is up to dot dot dot. So, I is equal to 1 to. So, if AI belongs to C, AI belongs to C for all I at 1 to dot dot. So, this is infinite, countably infinite collection of subset of A. So, those are inside C. If it belongs to C, then union of AI, if you take the union I is equal to 1 to infinity AI, that also belongs to C. So, that are the three conditions. So, if these three conditions are satisfied, or the three properties, following properties are satisfied by this collection of subset of A's, then C is known as sigma field. So, this is sigma field. So, for example, if you consider suppose this collection of subset of, because it is also a collection of subset of S, then you can see that S belongs to C and only S. So, that is why we have to consider if A belongs to C, that means S and phi are the only elements in C, then we have to just check those subset of C. So, those subset of S, those elements only we have to consider to check these properties. So, if so that is why if you see that S belongs to C implies S complement. What is S complement? S complement is nothing but null set. So, that is also belongs to C, because here we check that. Also phi belongs to C, also phi complement also belongs to C. So, this property is also satisfied by this C. Now, here this condition A1 A2 infinite collection. So, if infinite collection, but here only two sets are there. So, if you take the union of those S union phi, then also it is belongs to C. So, that is why because it is infinite collection in C. So, if you take any finite collection, that is also will be belongs to C, because remaining said you can take the phi, and then by this property this condition also will be satisfied. So, here also you can see that if you consider infinite collection like A1 equal to S, then phi like this. So, infinite collection of element in C like that, then you take union, then union will be nothing but union S union phi, S union phi like that. That also belongs to C, because this is nothing but it is which belongs to C. So, that is why this is a sigma field. This is a sigma field. Now, if you consider this collection C2. So, now for this C2 you can see that S is belongs to C and then it is satisfied. Now, we have to check the second condition. Second condition, it says that if a element A belongs to C, then it must imply A complement also belongs to C. Now, for S complement is phi, it belongs to C, no problem. For phi belongs to C, but phi complement, that is nothing but S also belongs to C. So, this is actually we are considering C2. So, we have to think that C2. So, this also belongs to C2, then this also belongs to C2. Now, if you consider this set A is equal to this H, now this is belongs to this collection C2. Now, if you consider the complement of that, what is the complement? Complement of H is nothing but, because S contains H and T. So, if you consider the complement of H, this is nothing but the set T. So, we did not include it in this set. We did not include it in this set. So, that is why this C2 this property not satisfying. So, this is not a sigma field, because for sigma field this three property has to be satisfied. So, this is the sigma field. Now, we will discuss what is measurable function. So, let us consider another sigma field. So, suppose you are doing a random experiment, rolling a die. Suppose you are doing a random experiment, you are rolling a die, then what will be the sample space? Suppose we will denote this sample space as S2 this is nothing but 1, 2, 3, 4, 5, 6. Okay. So, another thing I just want to mention. So C2 is not a sigma field, we found that. Now, if you what was the problem? The problem is that this A, whenever we are considering A is equal to H, this complement does not belongs to T. So, now we want to suppose we want to make this C2 as a sigma field, then what correction we have to make? So, keeping all this set, all the elements in this set, we just want to add more subsets of S such that it will be a sigma field. So, how we can do that? So, suppose let us later we will discuss this. So, let us keep here, then we will discuss this. Suppose C2 we just take phi, then S, then we have taken phi, and then the set head, then S. Now, the complement also we are adding this T. So, let us see that it is a sigma field or not. So, then you see in that case, here you can see that this property will be satisfying. So, basically here we are adding, here we are taking more element we will want to add. We saw that it is not a sigma field, we want to just add here T also. So, then you can see that for element H complement is T, it is also in C. So, if now if you have add this T, then T complement is H, that is also in the C. Now, if you take any union, finite union, or if you include there is no infinite collection, if you take distinct element. So, you can repeat those things. So, infinite collection we just mentioned that finite things also it will be, if this property is satisfied, then for finite collection also it will be inside C, this condition also will be satisfied. So, here we want to see that, because if you take all this kind of union, H union T is nothing but S. So, S union phi is S. So, then you see that all possible union, if you consider, it will be in C, whatever. So, that is why it will be this C2 also will be a sigma field, because this third property is also satisfied. So, this set actually this should satisfy, because if you consider all possible subset of S, then that possible subset, because it is a finite set, will contain 2 to the power n number of elements. So, 2 to the power 2, this is nothing but 4. So, C2 also contain 1, 2, 3, 4 subsets. So, that is why it contains all the subsets. So, all the subset is considering, so it is known as power set. So, it is known as whenever you consider all subsets. So, if C contain, if let S be a non-empty set, then suppose let omega denote set of set containing, omega denote the set, omega denote the set containing all possible subsets of S. So, S be a non-empty subset, let omega denote the set containing all possible subset of S. So, the set omega is known as power set. So, power set means it contains all subset of S. So, obviously power set is a sigma field, because power set will satisfy all these properties. So, S belongs to C, A belongs to C, A complement, because all the subset we have included there. Now, so C2 is a power set, C2 is a power set. Now, let us next we discuss this example, random experiment rolling a die, and then this is a the subset is a non-empty set S2. S2 is the sample space corresponding to rolling a die. So, it contains 1, 2, 3, 4, 5, 6, 6 element. So, if you consider the power set, then it will contain 2 to the power of 6 number of element in the power set. Now, let us consider not power set, some non-trivial sigma field. So, let us consider one set A is nothing but 1, 2 and 3, and another set B is nothing but we can consider like that. So, let us consider some kind of some meaning is there of this set. Suppose consider the even number 2, 4 and 6, and B is the number 1, 3 and 5. Sorry, B is the set subset of S2, B is nothing but 1, 3, 5. So, you can see that. So, now we want to find a suppose sigma field generated by, we say let us consider one some collection of subset, suppose C2 is here. So, we have already denoted C2, let us consider this is S1 and then let us consider this is C1. So, C1 is nothing but just the set A only subset. Now, note that it is not a sigma field because S is not inside here, phi is not, so S complement not here, A complement not here. So, we want to make this sigma field, we want to add more and more sets. So, we say sigma field generated by C1. So, we will take what are those properties here we want to include. So, sigma field generated by C1, it is nothing but this will be, we have to include A is there, A complement we have to include, see that A complement is nothing but B, and then S we have to include and also null sets. So, this is the sigma field generated by C1. So, you can add more sets also, so that it is a sigma field, but it may be we consider it is a smallest sigma field generated by C, because if you remove any of the subset here, any of the elements here, then it will not be a sigma field. So, it is called smallest sigma field generated by CR. So, this is a sigma field. So, basically A complement is nothing but B. So, A, the set A, B, it is a sigma field. Okay. Now, we want to define, so there are two sets sample space are there. So, S1 is one set. So, S1 is, so let us consider S1 and C1. C1 is, let us denote sigma field. So, C1 we consider this. So, let us denote this is nothing but F1. F1 is the sigma field generated by this C1. So, and also so let us, so S1 F1 is the, sorry, F1 is the one sigma field, it is a non-empty subset and this is the sigma field, and S is nothing but the head and tail we talked, and this C already we have discussed that C is nothing but, we consider here you can see that C is nothing but the null set and S. So, this is another, or we can consider C2, this is the sigma field also we can consider. So, no problem, let us 1 minute. So, yeah, so let us consider C2 is like this, S and C. Now, this is also sigma field, this is also sigma field. We want to define, so this notation is we want to dip the script F for, it is the standard notation. So, here also this is script F, it is not the small f. So, now we want to define a function between S1 and S, some function f is S1 to S, some function we want to define. So, we can define any function, suppose what S1 is, so S1 is nothing but it contain, this is the, suppose S1 is contain 1, 2, 3, 4, 5, 6, and S2 is, sorry, S is the element H and T, 2 points, 2 elements are there. Suppose for all even number we want to map to head. So, or let us consider a constant function. So, if you consider a constant function, suppose f of any element in S, S1, or suppose x f of x is equal to just h. So, this is a function. So, it is nothing but, so for any x belongs to S1. So, S1 is the, so just this is the function I am defining. So, basically all point actually going to h. So, this is a constant function. Now, you just check that we want to check. So, what is C? C contain just two elements. So, you can remember that C, what we take C? C is phi and s, phi and s, phi and s. So, then I just want to find what is f inverse of phi. F inverse of phi is defined by all x belongs to the space, this set S1, such that f of x is equal to f of x, this number is belongs to the set, belongs to the phi. So, now you can see that it does not contain any element satisfying this, because f of x belongs to, so phi means it is null set, none of the, but f of x is h for any x. So, this will be again a null set, null set. So, that is why, but this null set is belongs to this f, you can see that. Now, if you consider another set in C, so f inverse of suppose C, so this is all x belongs to the element in S1 such that f of x belongs to C. So, what is C? So, C we know that all the on minute. So, we just, C is a sigma field, we want to take this set S. So, we want to take another element of C. So, that is why I just notationally it is wrong, it is S actually, all element belongs to S. So, note that if you consider x such that f x belongs to, now what is f x? F x is h and S is contain h and t. So, for any x if you consider here, any x if you consider in S1, then f of x has to be belongs to S. So, that is nothing but all x it is satisfying. So, all x means here it is nothing but the all S1, and this is also belongs to the sigma field f. So, you know that you can see that for this function f, if you consider any element in this sigma field and if you take the inverse of that, and then that is belongs to actually this sigma field. So, this kind of function known as this function known as so let us write here, known as measurable function. So, what is measurable function? Let, so measurable function. So, what we understand the measurable function? Let suppose let us denote S1, F1 and S2, F2 be two sigma field and a function f from S1 to S2 is said to be measurable function if for any element b belongs to F2. So, that means this, so this notation it should be script f. So, it is not just, because otherwise you will confused with the usual functional notation. So, F2. So, for any element b belongs to this F2, f inverse of b that is belongs to F1. So, that means if you take inverse of this, so f inverse of b, how it is denoted? So, f inverse of b, it is nothing but all x in the S1 such that f of x belongs to B. So, this is called the f inverse B, it is denoted. So, if this is belongs to f1, so for any B belongs to f2, if because it is S1 to S2, then it is known as measurable function. Okay. Now, we will discuss a special kind of sigma field. So, because these are all little bit of abstract, head, tail, throwing a die. So, this will be 1, 2, 3, 4, 5, 6, that is a real number, but most of the phenomena in the real life we describe by some abstract type of, not, it may not be a real number. But if you find the observation like a real number, or we can relate it with some kind of real number, then it will be very helpful for us for understanding it. Because in the real number we have learned many things, like most of the algebra from our school life, college life, many algebraic properties, multiplication, addition, subtraction, not only that, limit, continuity, sequence, series, all those things already developed in the real number system. But if you take any abstract set, so we need to develop those things. It may be done, it can be okay, but we have to again verify it, or we have to develop all those concept or all this result with what we want to use it. So, if you can relate it with this kind of abstract set, because sample space is most of the time it is a abstract. So, like head, tail, for any event like earthquake. So, how you can relate with this with the real number, then only we can understand it, or we can make the computation. So, we want to learn some special sigma field, special collection of subset of the real number. So, if you consider this suppose real number S, suppose this set, because we are considering non-empty set.